All right, I just want to do a quick sound check. Is my sound okay?
Yes, you sound great.
Okay, all right, fantastic.
Hello and good morning, everyone. I think I'll give it just another couple of minutes because I see a number of people logging on. Good morning, good evening, I should say. So I think we will go ahead and get started. So welcome to the Joint Initiative for Causal Inference Spring 2021 webinar series. I'm Maya Peterson. I think I have met many of the people on this webinar, but perhaps not all. I'm on the Faculty of Biostatistics at the University of California, Berkeley. So I'd like to welcome everyone today for the next issue in our webinar series in the exciting joint initiative between the University of California, Berkeley, Novo Nordisk, and the University of Copenhagen. A bit about the joint initiative before we get started. This was launched about a year ago with really this vision for increased and better use of data for evidence generation. So really the mission of this initiative is to work to expand the knowledge and practice of sound scientific inference anchored in a causal roadmap, and then to continue to develop and disseminate methodology that makes it easy to apply really best practices rigorously. So the initiative has a number of objectives. We're engaging with regulatory agencies, industry, and other partners for the use of the causal roadmap, including targeted machine learning, to really give ourselves better inference or better answers, more rigorous answers with more precisely quantified uncertainty for real sort of pressing health questions. We want to work with clinicians to inform best practices around causal inference, including causal inference when you can't rely on randomization. And we're also working to showcase scientific potentials of causal inference based on observational data, including working with the Danish registry data and extending software to facilitate the use of causal inference following the causal roadmap principles. So a bit of an overview about our upcoming spring webinar. We are very excited about the webinar, and we're having session 1 today, kicking off on the topic of competing risks. So first, we're going to have Dr. Søren Rasmussen, who will give us an introduction to some of the challenges posed by competing risks. Dr. Thomas Gerd will then provide introductions to challenges from an academic biostatistics perspective. David Chen is then going to present on current methods and problems in handling competing risks, including discrete time, targeted maximum likelihood estimation, looking at simulations and also results from the LEADER trial. After that, Dr. Helene Rietgaard will introduce novel methods for competing risks, moving to continuous time and one-step targeted maximum likelihood estimation. And we'll also talk about applications. And then finally, we'll be sure to leave Q&A session time for all the presentations. And again, I think our vision with this webinar was one, kind of in line with the objectives of the joint initiative, really to work to sort of broaden the shared community of best practices in causal inference and create a venue for discussion of some of the methods that are coming on board. And to that end, we thought it would be nice to as well have a venue where work is being presented that is far advanced, but not totally complete, to really have a chance to as well get input and thoughts from the larger community about directions, current directions, future directions, and ways to improve things. So this will be our competing risks session today, which I'm quite excited about. I'll close at the very end today with just a few words about our future webinars coming up in the following months. And so without let's see. Oh, just a note on Q&A format. So as we do the talks, please go ahead and feel free to type any questions into the Zoom chat or the YouTube live chat, and we will have a moderated Q&A at the end of the talks. Any questions in the Zoom that we don't address in the allotted time, we will be sure to answer later. And so without further ado, I'm delighted to hand it over to Dr. Rasmussen.
Yeah, thank you. I hope everybody can see my screen. Many thanks for this opportunity to give some views on competing risk from a clinical trial perspective. A basic definition for competing risk is that it hinders observation to happen, and the most obvious example is, of course, death of all causes. You can almost call this the generic example of a competing risk, as what would happen with, for example, a hazard of first MI if death would not occur. But of course, competing risk could be more complex, as the second example implies. If you're interested in time to death on dialysis, then if a group of patients would get a kidney transplant and taken off dialysis, then that would preclude time to death on dialysis. More complex scenarios can, of course, be envisaged, and it is a subject matter what would be the relevant choice for a competing risk or informative censoring. This slide should illustrate that I think there is now a trend of moving away from homogeneous trial population to more complex trial population in terms of, for example, age and coexisting comorbidity. Hence, competing risk is more of an issue now than in the past in a clinical trial setting. In terms of competing risk as death, this could, of course, complicate things. If death is rare, then it's not something you would take into account estimate-wise. This is just perceived as a dropout, and missing values are imputed, disregarding this in the treatment policy estimate. For the large cardiovascular outcome trials, the endpoint is often major cardiovascular event, which includes cardiovascular death, such that non-CV death would be a natural candidate for competing risk. In terms of new therapeutical areas like, for example, heart failure, where death rates at 1 year could be as high as 5 or even 10%, then more soft endpoints like quality of life measures could be a complex endpoint in terms of competing risk. How should you take death into account in a treatment policy estimate if you would like to preserve a familiar statistics like, for example, mean change from baseline? As alternatives, non-parametric statistics could be proposed, like the win ratio in the quantitative version or other rank statistics, where death could be given a virtual low rank. An example of a quality of life endpoint is touched upon later in this talk. In time to event analysis, this influential paper from Fine and Gray in 1999 in YASA, as most of you know, introduces the sub-distribution hazard, and 20 years later, this has become an integral part of analyzing time to event data with competing risk. The second paper on the right, this is one of many, gives recommendations on how to handle competing risk in clinical trials using the methods from the Fine and Gray paper. These recommendations or suggestions, they are pretty much listed here when competing risk is present. Essentially, the cumulative incidence function should be used as opposed to the Kaplan-Meier plot, and Fine and Gray regression should be used for prognosis and regressions on the cumulative incidence. In the next 3 slides, I will give you some examples of these suggestions and recommendations with some real data. First example. This plot shows 2 arms in a clinical trial. That is a large CV outcome trials where we have an active arm and a placebo as a comparator. The both lines are the 1 minus Kaplan-Meier estimator, and the dotted lines are the Olin-Johansen estimator applying time to all-cause deaths as competing risk. The Olin-Johansen estimator is used for the cumulative incidence function, which is basically the KM estimator weighted downwards depending on the timing and number of competing events. The 1 minus KM estimator can be considered as an approximation to the cumulative incidence that may be used if the competing risk is small. However, the best guidance is never to use the 1 minus Km in the presence of competing risk. If one would show statistics on this plot, one could then use the treatment hazard ratio from the Cox regression and correspondingly the subdistribution hazard ratio from the fine and gray regression. These ratios are not directly comparable, where the latter can be interpreted as the treatment effect on the cumulative incidence function. As the all-cause mortality rate is low in this example, approximately 9% during the trial, then there is not much difference between the 1 minus Km and the Olin-Johansen estimator. Next slide. If we now change to an index of kidney impairment using the estimated glomerular filtration rate, also known as the EDFR, below 60, then risk of death is higher in this group, and hence the difference between the 1 minus Kaplan-Meier and the Olin-Johansen also becomes greater. Also, there seems to be a larger treatment effect in this subgroup. Last example, this is the cumulative incidence functions across a measure of EDFR. And here we use the fine and gray model to estimate the cumulative incidence function across the continuous EDFR using a spline regression and compare with a corresponding Cox regression. It can be observed the differences between the Cox regression and the fine and gray model is large, while the risk of death is high, that is at the low EDFR values on the left side of the plot for both arms. All these plots are made in SAS, that in recent versions of the STAT package has updated the possibilities to perform analyses taking competing events into account. Time to first event is the primary endpoint in most cardiovascular outcome trials, but attention has also moved to analysis of recurrent events as a measure of the total burden of the disease and has, of course, great interest for payers also. In this paper on the left side, we have reanalyzed first and recurrent MACE, that is the first and recurrent stroke and first and recurrent MI in the leader trial together with CV deaths. Interestingly enough, there is a parallel situation here where you have an Olin estimator for the estimated cumulative function for the recurrent events, not taking into account competing risk, as compared to an estimator called the Causal estimator, taking into account competing risk. And in this case, it is non-CV deaths, as we have CV deaths in the endpoint. The differences between the two estimators can be seen in the plot to the right. And these two estimators can also, by clever settings, be applied in the SAS PROC-PH procedure. Also, please note that this can also be applied to, for example, different adverse event groups with first and recurrent events, not just as in this example, adjudicated hard endpoints. And we can do that, of course, in all trials, and especially the CV outcome trials where competing risk should be considered taken into account. In the analysis of the current event, you can also use a parametric model consisting of two processes. One process analyzes the time to event of interest, and another process analyzes the time to the competing event, for example, all-cause death. These two processes can then be correlated using a subject-wise frailty, that is a random effect model. And these models are also called shared frailty models for recurrent events and a terminal event, at least originally. These models, of course, have a lot of parameters. for example, you have a random effect for each subject or patient in a trial and are computationally intensive, and sometimes conversion problems in the estimation algorithm can appear. Hence, you would argue that these models are quite the opposite in terms of robustness as some of the models which are presented later in this webinar. I will not show any result for these models in the current event setting, but the idea is to show some results for longitudinal data. These models are also called joint modeling. They have two advantages. You can take into account competing risk, and also you can model trajectories across visits for each subject, for example, using random slope models in the time to competing risk event processes. So this slide addresses the problem with the estimate mentioned earlier for quality of life scores, where non-parametric modeling could be an alternative for incorporating deaths imputing those as the lowest ranks. But here we have KCCQ, that is a quality of life score as a continuous measure, and higher KCCQ is better. And it is a quality of life score used in, for example, heart failure patients or other cardiovascular disease patients. This score has also a regulatory interest as it is associated with fewer hospitalizations and deaths if you have a higher KCCQ. When this is a competing risk, you could discuss if patients would have a different trajectory as opposed for those observed. This is, for example, illustrated by the standard of care arm, where the mean trajectory is more steep, taking all-cause death or all-cause mortality into account using the joint Bayesian model. And you should not be scared of the Bayesian modeling used here, as it can be implemented outside the Bayesian framework. That was, of course, a small joke. What is interesting here is that comparing the original longitudinal growth model with the model taking into account of all-cause deaths, the already impressive treatment difference is actually increased with more than 5 points, as you can see on the last row in the table. These 5 points, they are actually considered clinical relevant. But please note that this is a quite extreme example where the hazard ratio for all-cause death is 0.5 for the active comparator versus the standard of care. And hence you see this quite impressive effect, at least potentially using the joint model. A more, you can say, modest example using leader data, which is also using joint modeling, is the slope of EGFR, as we looked upon before, where more negative slopes is associated with poor renal function. Here, the competing risk is all-cause death or end-stage renal disease. If you take into account these competing risks in the slopes, you're getting more negative steep slopes as compared, that is the light blue ones, as compared to the usual random slope models. So the light blue is the results from the joint modeling, taking competing risk into account. And you can also see this is more pronounced in the right panel, in the subgroup of patients with the poorest renal function, where the event rate of the competing risk is, of course, largest. The joint modeling did not change the treatment differences in the slopes here. So it is more an example of how the slopes are actually getting more steep. One last example from the literature, and it's just a simple summary table of different characteristics of the adjudicated myocardial infarction. When you quickly glance in the summary table, there seems not to be much difference between the characteristics for liraglutide as compared to the placebo. If, for example, look in the bottom of the table, you can see that there is slightly more subjects with a troponin value below 5 in the liraglutide group versus above 5, which indicate that the myocardial infarction are less severe. but it's of course not significant at a 5% level. One could then speculate, as there is a significantly higher risk of CV deaths in the placebo arm in this trial, if some of the most severe MIs is not counted in the placebo arm, a CV death could be a competing risk. And hence, this is again a classical example where you could take competing risk into account. Last slide. Don't know if I should call this conclusions, but anyway, what I think is that sometimes competing risk is not easy to identify in some clinical trials. I have in this presentation maybe presented the most generic examples, and I think the next presenter will touch upon more complex scenarios and the underlying reason. Also, I think that competing risk is somehow entangled in the discussion about different estimates, most notably in the joint modeling examples, where one could take into account competing risk, where you don't have any observed value after the competing risk event has occurred. All the examples I have presented here could be implemented in SAS, which would encourage more to pursue application of taking competing risk into account in pharma. And now that it's very easy to implement, for example, cumulative incidence function in SAS, as opposed to use the Kaplan-Meier plot. Also, joint models could easily be implemented in SAS. Yes, I will end my talk here. Thanks for the attention.
Wonderful. Thank you so much, Søren. So I know we sort of said we'd have a Q&A at the end, but I think we do have a few minutes available now. So just any comments or questions? I think there was one from Torben in the chat before we move on to the next talk by Dr. Gerds.
And that question from the chat was, it does not make sense to compare Cox models for cause-specific hazard and the FG model. And Torben can expand on this of interest.
Okay, I will take that into note.
Oh, Torben, did you want to say anything more about that, just as a comment, or?
Yeah, I can expand a bit on that. Well, the fine and gray model is a regression model for the cumulative incidence function, and the cumulative incidence function consists of both cause-specific hazard functions. So it sort of mixes up both cause-specific hazard functions into one function. And but still, you can see it as a regression model for the cumulative incidence function. The parameter is very weird. You cannot really understand them because it's those strange hazard ratios that you get out of that model. I don't think anyone can understand them in a sensible way, because you're still at risk when you have sort of died. But the problem, so from that perspective, it may be more tempting to try to analyze the cause-specific hazard function. But we know now that cause-specific hazard function doesn't have a causal interpretation. It doesn't have a causal interpretation in ordinary survival analysis. And it's even worse for competing risk data. So there's still room for development here, I guess. So a more modern approach.
And a beautiful segue, and I think thanks for that, Torben and Søren. I think you also made that point nicely in sort of emphasizing the importance of getting straight about our question and our estimand before sort of proceeding. And I think so both of those are maybe a lovely lead into our next speaker. So next we'll have Dr. Thomas Gerds of the University of Copenhagen.
Okay, can you see my screen and hear me well?
Yes.
Good. Okay, so I'm talking about competing risks. My first subject is competing risks are everywhere. Then I have a...
Sorry, Thomas, I don't see your slides. I see, I think your desktop background.
My desktop background, oops.
It's really cool.
It is really cool. Yeah.
Yes, I once knew what it meant. It's some Chinese message. That's strange. No, I can't find my. Okay, here. I think I have to go here. How's that?
Very good.
No? Okay.
Yes. Yeah.
See the outline?
Yes.
Okay, thank you. Okay, so competing risks are everywhere, then false money and the discrete superlearner. These are my three subjects for today. And the first, I want to give credit to my colleague and friend Per Krag Andersen, who taught me a lot about competing risks. And when you listen to him, then it's not a very difficult problem. And yes, he said that if we were to write a book about this subject, then it would be a rather thin book. But that just means that Per is very clever and he understood all these things many years ago. So we have to catch up and see what's going on. So the competing risks happen everywhere, because whenever we study the life of a person, then death is a natural competing risk. And that means that whenever we study either a time to event, or if we study a time series of a biomarker or similar, then these will be truncated by death. And by definition, the competing risk is an absorbing state where nothing can happen after the competing risk. But as we will see in my discussion, it is also sometimes subject to discussion with the subject matter whether something is a competing risk or not. And it depends on whether we are interested in what happens after the competing risk has happened, or whether we are not interested in that. And when we now go to the applied part, so the medical research, then I think competing risks are quite often even by patients understood in a quite intuitive manner. And that is, for example, when we tell someone that the probability of death and the probability of dementia, then of course the person is mostly interested in dying without dementia happening. And of course, death shouldn't happen very soon, but we want to expand or prolong the period in which we are dementia-free and alive. And we're interested in which type of treatments or pills or other interventions would increase that period. Now, when we talk about competing risks, we need to show a model like this, and I will show more models like this later on. But this is a good example because it has been used extensively in the statistical literature. So the data were published by Ternot, and I think they're also part of the counting process book by Fleming and Harrington. And as a result, we saw enormously many papers using this data set as an example data set. And why is this data set so interesting? It's so interesting because the first many years where this data set was available in R, the liver transplant, so these are patients who suffer some disease which apparently has been renamed. So disease is called primary biliary cirrhosis. And then two things can happen: death without a transplant or a liver transplant. But in the first many years where this data set was available on R, the liver transplant patients were coded as censored. So that meant that many covariates had a strong effect on the censoring just due to these, let's say, 19 patients who were receiving a liver transplant. So there was information in the censoring, and that was interesting for the statisticians. But since 5 years or something, this has been recoded. So now liver transplant has its own value. And other examples, competing risks happen everywhere. Other examples that I've been working with where tooth loss is a competing risk for time to failure of a dental filling. And these are complicated data because the observation is interval censored and there are multiple subjects within one mouth, so multiple dental fillings within one mouth, so extremely complicated data structure. Then we could discuss non-cardiovascular mortality as a competing risk for whatever cardiovascular event we're interested in. We should, we could discuss whether treatment-related mortality is a competing risk for relapse in cancer, but that is not a discussion because that's quite clear. However, the discussion is more intense when we discuss whether discharge from intensive care unit is a competing risk for death within ICU. Of course, it's a competing risk for death within ICU, but it's not a competing risk for death anywhere. And then a positive outcome would be pregnancy, and there menopause is clearly a competing risk. So these were many examples that I've been working on, and there are certainly many more out there, and it happens more often than it doesn't that there are competing risks. Then there are also intermediate events. And of course, stroke is not a competing risk for dementia in the sense that once you have had a stroke, then actually the risk of dementia is higher than before. So it's something like an intermediate variable. And we have certain working groups in this initiative where we just discussed the mediation problems. And I'm looking forward to solutions or to analysis of these mediation analysis. And then other things that are less clear is whether or not we want to treat stroke as a competing risk for myocardial infarction or the other way around. So I've been co-authoring many applied papers where we were analyzing the risk of stroke, where death not due to stroke was a competing risk. And then in the same paper, analysis of the risk of myocardial infarction, where death not due to myocardial infarction were the competing risk. However, they were not treated as competing risks for each other, so stroke and myocardial infarction. And then another thing that is, needs a lot of discussion is what happens if some patient changes the treatment. And then we could, of course, call that a competing risk. But in many cases, we would rather like to estimate what would have happened had the patient not changed the treatment. And we have other sub-projects in our initiative here where we are looking at drop-in and drop-out and so forth. So very interesting analysis to come. Okay, I would say that most generally an event can be considered a competing risk when baseline information is insufficient to treat the event as censored. And now here, I'm not talking about death, but I'm mostly talking about other things that are not absorbing in the real world, where we have to make the decision of whether to not to take it, use it as a competing risk. Okay, so I want to briefly touch upon the false money issue here. And I think there I want to clarify what I think is the definition or the distinction between competing risks and censored data. And you can see here two pictures, both from Tour de France. And if we're interested in the speed or the time to arrival of these bicycle riders, then for sure, what we see on the left-hand side, that's a competing risk, because after this accident happened, this rider will not continue riding and the arrival time will never happen. So this rider will never arrive at the final destination. However, on the right-hand side, something else happens. It's not the rider who has the accident, but it's the motorcycle who is filming and taking care of the follow-up of the rider. And if the follow-up stops because the motorcyclist has an accident, then of course we have a censored observation because the rider will continue no matter what happened to the motorcycle. We just don't observe this. So the difference between censored and competing risk is the observation, yes or no. And another example here is, so it's very much censored, is very much what you have in a newspaper. So when you have some statement, then you can have a competing risk. And that's what we have here on the left-hand side from the famous problem of Fermat. There, the competing risk was there was not enough space in the margin of the book to write the proof. And that's a competing risk, of course, whereas censored would be if we had some black stripes here and we couldn't read what was written under these black stripes. And you can maybe already feel here is some kind of discussion whether what we have on the left-hand side is a competing risk or could be treated as censored. So it's always a subject matter discussion that we have going on. But all of this is very much related to the discussion of whether we can use 1 minus Kaplan-Meier. And we have heard earlier that one should not use 1 minus Kaplan-Meier, but there are some other researchers out here, and this was a discussion with an experienced epidemiologist, and he was writing emails to me and I was writing emails back, and here we're discussing prostate cancer, and we see here what my colleague here argues that in prostate cancer, it's almost true that no one dies of other causes than the prostate cancer. And using competing risk or just censoring at the date of death makes no difference. And then I was not happy with this statement, and I replied, and here's the reply to my reply. So he disagrees that there are correct and mistaken methods and complains that methods for competing risks are not very well understood, and also that the computation time when you have a competing risk analysis is much longer as compared to when you do not have a competing risk analysis and so forth. And then at the very end, he actually provided a data set. So I could have a look for myself. And what we can see here is that we have a competing risk data set with prostate cancer, and death is the competing risk for the Olin-Johansen estimate. And that's the black line, and the red line is the 1 minus Kaplan-Meier. And we see that true, in the first 5 years, we can hardly see a difference. But this is what I call the false money argument. So when you now were to report the result after 5 years, then choosing the Kaplan-Meier is very similar to having real money and false money in your pocket, and then choosing the false money instead of the real money. So I'm not buying this computation time argument either, because nowadays computers are very fast, and there are very fast algorithms that compute the real thing that takes into account the competing risks and doesn't generate a hypothetical world in which no one is interested. Okay, and regarding the confusion and the many discussions we have out there, I wanted to clean up with 2 terms that I really do not like anymore, even though they are everywhere. So at risk, that's a term that we use all the time for describing how many people are there, patients are there at risk. That's what we have under every Kaplan-Meier curve, on every Olin-Johansen curve. But really, the term is a bit misleading because it's not at risk of the event. It's to be at risk of the event and to be observed to be at risk. So you have to also be uncensored. And that is I think that's quite misleading, this term. So this full expression would of course be too long, but some people who have not learned about this distinction, they should be aware. And the other term I don't like is the term cumulative incidence. Cumulative incidence can be either a cumulative incidence function or a cumulative incidence rate. And these 2 things are completely different things, and shorthand cumulative incidence doesn't make that very clear. And I prefer to put a different term on this one. It's the absolute risk of event of type 1 between time 0 and time t. I think that's the term absolute risk of the event. That's a better event of interest, or type 1 event. That would be a better term than cumulative incidence. Okay, and then of course all this terminology is much older, but has been partly forgotten. So this here is a paper from 1961 about the life table, and here they were discussing the differences between net probability, crude probability, and then also partial crude probability. So the net probability would correspond very much to this hypothetical world, which one generates when one uses 1 minus Kaplan-Meier. And the crude probability is what we are estimating when we're using the Olin-Johansen estimate of the absolute risk of the event of type 1 in the presence of all the other risks in the population. And then suppose they're not just 2, but maybe k different causes, then the partial crude probability would be in a hypothetical world where one or several of the competing risks were eliminated from the population, but we are still interested in estimating the risk of cause k in the presence of those risks that were not eliminated. So I think we all need to also go back to the old discussions when we want to understand the situation, because they were quite far already in the 60s. Okay, the final subject for today is the discrete superlearner. And here I want to first make the statement that for medical decision making, we should usually have estimates of all the absolute risks of all the competing risks simultaneously. So not only F1, but also F2. And we will hear later about how that can happen, how we can estimate both at the same time. So that I think is progress. And we need to just be careful because the interpretation is also important. And interpretation is very much explained when we discuss multi-state models. So this is not a DAG. An arrow just means there's a possible transition. So from state at inclusion, we can have a stroke, and after the stroke, we can have death. But after stroke, we also can have a myocardial infarction, and after that, we can have death, and so forth. So these multi-state models, they're quite useful in order to discuss what the event of interest is. And we should note that censored is not a state. So the definition of multi-state model is that at any time, every patient is in one of these states. And censoring just means we do not know in which state this patient is. We have lost follow-up. Okay, from this complicated 4-state model, we could decide to analyze a competing risk model with 3 outcomes and then the time to what happens first. So it would be time to stroke or myocardial infarction or death. But here it would be death without myocardial infarction and without stroke. So the interpretation of death is not the usual interpretation of death. We could as well decide, okay, there are only 2 causes. We don't care about myocardial infarction. We say we are interested in the probability of stroke with the competing risk being death without stroke. And when we want to then, after we have decided about the outcome event, we want to discuss modeling, then we meet what we see in the medical literature. We meet a lot of confusion. So many people think that when there are competing risks, then Cox regression is wrong. And they believe that Fine-Gray regression is right. And the truth is that statistical models such as Cox regression and Fine-Gray regression can be used to enter into the library of the discrete superlearner in order to make, for example, initial estimates that can then be used for causal inference. So neither of these directly has a nice interpretation that we are interested in this initiative. But to make things clear, we have the typical formula here for the cause-specific Cox regression. We have the absolute risk of event type 1 expressed by the typical formula, where we see the 2 hazard rates enter the hazard rate of stroke and the hazard rate of death due to other causes without stroke. And then if we are into Cox regression modeling, then we have to specify 1 Cox regression model for the hazard rate of stroke and a possibly different Cox regression model for the hazard rate of death. And in that way, we could obtain predictions of the absolute risk of event of type 1 within time t for given patient X. And the combination of the cause-specific Cox regression models has the advantage that we can think about the biology when we choose the X variables together with the subject matter experts, because then we are talking about effects on the cause-specific hazard, and here we can think directly about the biology of the disease. And we have to accept that changes of the covariates that change the absolute risk of stroke can either be due to a change on the hazard rate of stroke, or due to a change of the hazard rate due to other causes or even both. The fine-gray regression is just one example of a series of other possibilities. So we can do the fine-gray regression model. We can also do a logistic regression model in the competing risk setting. And we could sometimes do a log binomial model with the advantage that the beta coefficients would have a bit nicer interpretation as compared to the fine and gray and logistic regression model. All of these need an estimate of the regression function for the censoring times, so survival function for the censoring times, in order to do inverse probability of censoring weighting. And the discrete superlearner, I have an R package called risk regression. Here you can fit the cause-specific Cox regression model first, and you can have one formula for the hazard rate of event of type 1 and a different formula for the event of type 2. So that's interesting. And then we have the fine-gray regression model, and we could as well fit a random forest for competing risk data. And then the discrete superlearner can be obtained by comparing the tree using some form of cross-validation for a given prediction time horizon using some loss function. In this case, I'm promoting the quadratic loss function. And then there will be some inverse probability of censoring weighting going on in order to avoid systematic bias. And the final remarks here are regarding treatment. Of course, in this initiative, we are very much interested in estimating treatment effects. And here I want to name two different estimates. One is in the competing risk setting. And currently what we have implemented in our library is an estimate of each cause at the time in the counterfactual setting, where we look at the probability of event of type 1 within time until time t, in a hypothetical world where we had randomized treatment here to treatment and to placebo over here, and then we're looking at the difference. So we try to estimate this using the average treatment effect function, and here we're having some augmented terms in order to make it as locally efficient as possible within the limitations of Cox and logistic regression models. And obviously here we want to go further in this initiative and introduce the HEL estimator and make progress. Another estimate was discussed by Robbins and also by Torben Martinusson. He was working with Stenrud. And that is interesting because it's addressing the fact that when we have a treatment that increases the competing risks, so the hazard rate of the competing risks, then in this way, the treatment would immediately also decrease the risk of the outcome event. And the idea of the separable effects is that we imagine that our treatment can be split into two things. So imagine a pill which can be broken apart into two pills, and then one of them acts on the hazard rate of the event of interest, and we randomize this part, whereas we keep the other part of the pill constant. So the A here is 2 in both sides of the estimate, definition of the estimate, the same. And that, I think, is a quite interesting idea, and I think we should go and discuss this further in this initiative. Okay, let me summarize. So competing risks are everywhere, but they should not be considered after death. Then decision-making inference should usually target all the competing risks simultaneously, and whether or not something is a competing risk is a matter to discuss with the subject matter experts. And then I think we should be aware of the large body of and and use that when we discuss the outcome of interest. We need to observe for many of the methods that we are discussing all the events in continuous time. And for example, when we have stroke as the event of interest, then we should also get the information if death happens, whether the death was due to a stroke that had maybe happened on the day of death. And finally, the discussion of treatment is not as simple as it seems, because many of the things that we need to discuss when we analyze treatment effects are time dependent. And I think that was the last thing I wanted to say. Thank you for your attention.
Wonderful. Thank you so much, Thomas. So I think just in the interest of time, and because that's a beautiful segue into our next two talks, we'll just press ahead with the next talk from David Shen at Berkeley, and then we'll come back. I know there was a question in the chat. Maybe we can come back to the question at the end for all the talks. But thank you very much, Thomas. And David, go ahead.
Okay, let's see. Is my audio all right? And can everyone see the slides?
No, we see your
Desktop.
something
Okay.
with your browser. There we go.
Okay. Oh, I'm sharing the wrong desktop screen. Let's try this.
Perfect.
Yep.
All right. Okay. It's a little bit messed up on my end, but as long as everyone can see my slides, I guess it doesn't matter what I see. Okay. So I'll be talking specifically about analyzing competing risks using discrete time QMLD. I'll be walking through the process, as well as presenting some simulation results, and also a preliminary analysis of LEADER, where I consider some competing events there. All right, and so this wouldn't be a Berkeley biostatistics talk if I didn't mention the targeted learning roadmap. So, not to belabor the point, but very quickly, we want to begin with a causal question, right? Formulating a causal question, defining a causal model, and defining a causal quantity. And from this causal problem, we can move towards a statistical problem by defining a statistical model and a statistical quantity, and considering the necessary assumptions for our statistical quantity to identify the target causal parameter. And then after having a well-defined statistical problem, then we can move to estimation and inference. Our motivating data example is LEADER. So very briefly, LEADER was a multinational cardiovascular outcome trial. 9,340 patients were recruited, all of whom had type 2 diabetes and were at high risk for cardiovascular disease. They were randomized to either receive liraglutide or a placebo plus standard of care, delivered something from about 3.5 to 5 years. Drop-in treatments and treatment holidays were allowed, but we'll be taking an intent to treat approach, so those complications won't be addressed in the subsequent analysis. The primary outcome of interest in LEADER was MACE, which is a composite outcome comprising of death related to cardiovascular causes, as well as non-fatal myocardial infarctions and non-fatal strokes. Previously, in the last webinar series, we talked about alternatives to using the hazard ratio, but the theme this time is competing events. And so I thought, the natural competing event is, of course, non-CV deaths that are not related to cardiovascular causes. But it seemed pretty easy to break the composite MACE outcome into separate competing events also. And so I ended up with 3 competing events. The first is death related to cardiovascular causes. Second is non-fatal MACE events. And third is the death not related to cardiovascular causes. So with that, we start down our causal roadmap, beginning by defining the full data. Here is being represented by X. So X is comprised of W, which are baseline covariates, demographics, clinical measures like blood work, relevant clinical histories like histories of strokes and heart attacks, And then we have the set of 6 counterfactual times to events, right? So the superscript T superscript 0 indicates the counterfactual time to event if assigned to control, whereas T superscript 1 represents the counterfactual time to first observed event if assigned to the treatment arm. And the subscripts J indicate which of the events it is, whether it'll be 1 for CV death, 2 for non-fatal MACE, and 3 for non-CV death. And a causal question might be something like, does assignment to liraglutide versus placebo result in excessive relative risk of CV death, non-fatal MACE, and non-CV death at 12 months, 24 months, 36 months, and 48 months? So here I'm looking at 4 time points, 3 events, and 2 treatment specific risks. But basically, the parameter that I'm looking for is what I might call the counterfactual cause-specific, treatment-specific risk at time tau. But basically, that just means I want the counterfactual probability of observing an event J given a treatment A at or before time tau. So what this will look like is I'm actually interested in these question marks presented in these 2 tables. The top table is the treated cause-specific risks. So each of the columns corresponds with the risk for some event. The first column is our risks for CV death, event 1. The second column for non-fatal MACE, and the third column for non-CV death. And then each of the rows is a particular time point tau. So for instance, the top left entry here in the first in the top table would be the counterfactual probability of observing a death related to cardiovascular causes given treatment at or before or during the first year. And their corresponding values given control are in the bottom table. My causal quantity of interest defined here is simply dividing the top table values by their corresponding bottom table values. So if maybe it's easier for people to think visually, that might be one way to think about this causal quantity. Okay, so with that, I can move from the causal problem towards a statistical problem, and we'll begin again by defining the data. Our observed data, represented here by O, is comprised of W, which is the same baseline covariance as before, A, which is a binary indicator of treatment assignment. T tilde is the minimum of C, T1, T2, and T3. Essentially, it's the time to whatever happens first, censoring, CV death, the first occurrence of a non-fatal MACE or non-CV death, right? Time to whatever happens first. Delta is an indicator that censoring preceded any observation of any of the events. And J is which of the events occurred first. This observed data also has a longitudinal form where we instead follow the counting processes for each of the events. What this will look like is shown in this table here, where each individual will get T tilde rows as they'll be followed until one of their counting processes jumps to 1. Right. And at this point, I want to take a little side step to iron out some notation, which will make writing some of the subsequent distributions easier. So since I'm dealing with discrete time, I need to assume time ordering. And so I decided that at every time t, non-CV death will come first. It'll trump CV death, which will be non-fatal MACE, which will come before censoring. And then next I define parents, and there's a little dagger here. As I've defined parents as a subset of what is normally considered parents, I'm not including baseline covariance and treatment assignment here, so that it'll make it easier for me to write the formula for the indicator of risk later. But here, if we look at the parents for event 3, the parents for N3 of N3 at T, since event 3 happens first, it's just the histories of the counting processes of all the counting processes up till T minus 1. Whereas the parents for NC of T, since censoring happens last, are the counting processes, are the other counting histories of the other counting processes up till T, and the history of its own counting process up till T minus 1. Next, we have this indicator of being at risk, which I denote here with R. For mutually exclusive events, as is classical competing events, I can write something like Rj of T is equal to the indicator that the parents of Nj of T are all equal to 0. Essentially, an individual would be at risk only if none of the histories, none of the counting processes have jumped up till that time point. And there's a similar definition for Rc of T being at risk of censoring. So with this notation in place, I can write this factorization for the observed data density. The observed data density, so the data generating density P naught is equal to the marginal density of W times the conditional density of A given W times this product over time from T equals 1 up to T tilde of the product of the conditional densities of the 3 event counting processes. Ooh, recording stop. As well as, let me go back, as well as the density for the censoring counting process. All right. Yeah, all right. So what's next is we should be explicit about the assumptions that are necessary for us to be able to identify our causal quantity with a statistical estimate. So we'll begin with treatment randomization, or sometimes conditional exchangeability, many names. But the idea is that we want treatment assignment to be independent of the counterfactual outcome, conditional on W. We have a similar randomization assumption, a sequential randomization on censoring, which is that the censoring counting process is independent of the counterfactual outcome, conditional on the observed past. And then lastly, we have positivity assumptions for treatment as well as for remaining uncensored. Okay. All right, so at this point, given these identification assumptions, we can start with some identification results. For instance, for the post-intervention distribution, for a desired treatment level A and no censoring, this P superscript A is equal to the product of the density of the marginal density of W times the indicator of receiving the desired level of treatment times this product over time of the indicator of remaining uncensored times the product of these conditional densities for the 3 event counting processes. At this point, I want to point out, or I want to define cause-specific hazards in this way, because it's important to point out that these conditional densities for the counting processes have this binomial formulation here, where the cause-specific hazard acts as P. Right, and so the end result is that the post-intervention distribution is a function of the cause-specific hazards, as well as the marginal distribution of W, which we see here when I define the statistical estimand, or at least the component that'll go into making up of the actual statistical demand, which is down below here. And so the cause-specific treatment-specific risks, which I call here FAJ of tau, has this is identified by this G computation formula. It's the expectation with respect to the baseline covariate of the sum over time of the cause-specific hazard times the probability of surviving up to that time. The probability of surviving up to that time is 1 minus the aggregate hazard, or the product of 1 minus the aggregate hazard, and in the case of in the classic competing events case, it's just the sum of the cause-specific hazards. So with that, I now have a statistical estimand shown here down below, and given the identification assumptions of conditional exchangeability, sequential randomization on censoring, and the positivity assumptions for treatment assignment as well as for remaining uncensored, this statistical estimand identifies the causal parameter that I defined in the first place. All that's necessary to finish defining our statistical estimation problem is to state a statistical model. The statistical model, here script M, is the set of possible densities for the observed data O. And so we will be considering a statistical model that makes only assumptions on PA and the conditional density of the censoring class S. So a restatement of our summary of our statistical estimation problem now is that we've observed NIID observations O1 to ON that are drawn from a data generating distribution P0 that lies in the statistical model script M, and we will be estimating the target estimand psi P0 from this slide up here, which is this mapping from the model to R3. So now, having defined the statistical estimation problem, we move into estimation. And since this talk is using discrete time TMLE to analyze competing risks, that's what I'll be doing. I'll be using TMLE to perform the estimation. So very briefly, TMLE is a method for constructing efficient estimators in the class of regular asymptotically linear estimators. Using TMLE to update an initial superlinear ensemble estimate combines the flexibility of machine learning with valid asymptotic inference based on influence curves. There's also this nice doubly robustness property for consistency, especially when dealing with randomized trials. So TMLE, in a nutshell, is performed in 2 steps. There's an initial estimation step, and then there's an update step. So the first initial estimation step, what we want to do is let Q0 represent the portions of the data generating distribution P0 that are relevant for the target parameter psi of P0, and let G0 represent the portions of that data generating distribution that are not. Right? And then the initial estimates, we want to first get initial estimates Qn of Q0 and Gn of G0. Then we want to update Qn into a targeted Q star n that makes an optimal bias variance trade-off for the target parameter rather than for the overall density. And so this is all still quite vague, but in practice, in this convening of risk setting, let's consider the simple case of 2 competing events. Everything else that I've described earlier, our causal quantity, our statistical estimate, all that still remains the same. And so the first thing that I want to do is determine what are the relevant portions of the data generating distribution and what are the parts that are not. And so for our statistical estimate of this treatment-specific, cost-specific risk, right? I have this G computation formula here, which depends on the it depends on the marginal density of W, PW. It depends on the cause-specific risk, cause-specific hazards, lambda 1 and lambda 2 in this case, since I'm dealing just with 2 competing events. And so the relevant portions of P0 are the marginal density of W and the 2 cause-specific hazards. The nuisance parameters, the parts that aren't relevant, are the conditional density of A given W and the conditional hazard for censoring. Yeah, having defined Q0 and G0, I would then want to make initial estimates for these quantities. The marginal density of W can be estimated using the empirical distribution of the baseline covariates, which then doesn't get changed at all during the targeting. And so to keep the rest of the discussion a little bit simpler, I'll just be ignoring the marginal density of W when I talk about Q. So the next step is the update step. And from semi-parametric efficiency theory, we know that an efficient RAL estimator solves the efficient influence curve that's represented here. And so this targeting step in TMLE involves defining a loss function L of Qn and a fluctuation parametric working model parameterized by epsilon, which together produce a score that at epsilon equals 0 equals the efficient influence curve evaluated at Q and Gn. So this way, if we minimize the empirical risk with respect to this loss function, we'll solve the efficient influence curve. So specifically for treatment-specific, cause-specific risks, this first line here is the efficient influence curve for the cause-specific, treatment-specific risk. It has this form, this H star JA term here, we call the credible covariate. For each of the J's, 1 and 2, they have this formulation. So the efficient influence curve is defined here for the treatment-specific, cause-specific risk. This loss function, the log likelihood loss function, together with this fluctuation working model, together produce a score that is equal to this efficient influence curve. And so what we would then do to fit it is just do a logistic regression and update this initial cause-specific hazard into this updated cause-specific hazard. So to sort of review the process again, right? We want to start with initial estimates. The cause-specific hazards are the parts of Q that need to be targeted. The propensity score and the censoring hazard are the parts of G, our estimates of G. Right? Then in the update steps, we calculate Q star N, which are the updated cause-specific hazards, so that we solve the efficient influence function. And so this update step sometimes needs to be iterated multiple times so that we progressively update subsequent or previous updates until we get until this empirical mean becomes sufficiently close to 0. But in the end, we perform a plug-in estimate where we use the updated Q star N, which in our case are the cause-specific hazards, as plugins for Q naught in order to estimate psi of Q naught, which in our case is the cause-specific, treatment-specific risk. So with that, I think I move into implementation. And so David Ben-Kezer and Nima Hijazi, they wrote this package serve TMLE in R, which is was designed to handle competing risks. It's written to perform discrete time TMLE, targeting survival curves or risk curves at a single time point. It's written with competing events in mind, and also it can handle bounded incidents if there are rare outcomes. By default, it'll use pooled logistic regression to estimate the hazards, and you can also use superlinear to do that also. Here, it's still in development, but TMLE3, Jeremy Coyle and collaborators are working on implementing functionality for survival analysis and for eventually for competing risks. It'll be part of TLVerse, which is the targeted learning software ecosystem in R, and it was written from the ground up with the sort of targeted learning workflow in mind. And so it's even though it's not ready for survival analysis yet, for point treatment or for simpler problems, it might be something worth looking into if you're interested in learning. Okay, so here's a an example of what it might look like to use SERVTMLE to analyze a data set. As you can see, it's relatively short. You begin by loading the data, defining your adjustment set of your covariates. Here I define superlearner libraries for estimating the cause-specific hazards, censoring, and the treatment assignment mechanism. And then all that's left is to run SERVTMLE with the appropriate arguments. And SERVTMLE will return point estimates as well as influence curves as long as return IC is flagged true. And the influence curves will allow you to then to get variance and provide inference. Okay, so moving on to the data generation for the simulation that I'll present results for in a moment.
And David, this is great, and I definitely don't want to cut you short, but I just want to make sure we have enough time for our next speaker. So maybe hit the high points of the simulation and data results, just to make sure we have enough.
Yeah.
Great.
Yeah, absolutely. I'll be quick. I think maybe like 5 minutes from the end. So the first thing I want to say is just that the overall survival curves for treatment versus control are actually the same. And so this is, even though so if you're looking at a composite outcome, one might think that treatment has no effect, but in fact, treatment is actually beneficial for the first event, and it's detrimental for the second effect, thus creating that the same overall survival. There's also, in the simulation, also include informative censoring, and I'll be looking at estimating the treatment-specific, cause-specific risks at 12, 24, and 36 months. The estimators that I use are the Allen-Johansson G computation that is plugging in the superlearner estimates of hazards using a library of misspecified models, and then a TMLE using the superlearner as initial estimates. And so because we have informative censoring, we expect that the Allen-Johansson may be biased. The misspecified G computation is also likely biased, but TMLE should correct for that. And so we start here on the upper right. This is the control risks for event 1, and we see that G computation and the Allen-Johansson are both biased, as we expected that they might be, but that TMLE corrects for the bias in the G computation. We see a similar correction for bias when we look at the control risk for event 2, and Allen-Johansson actually does quite well. It's just that it's not guaranteed to be unbiased. When we look at the treated risk for event 1 and the treated risk of event 2, we see a very similar thing happen here, where the G computation and the Allen-Johansson are both biased, whereas the TMLE corrects for the bias in the G computation. Now, moving on to the leader analysis, right? This is just to remind us of, we start with a causal question, a causal parameter, go through the steps to identify the causal parameter with a statistical estimand. There's some estimation choices. So one important thing to mention that as this is a reason to use continuous time TMLE rather than discrete time TMLE, is that I had to coarsen the timescale of the leader data to 3-month intervals because there's instability when attempting to estimate small hazards. But that brings me to the results of the leader analysis. So just to remind everyone, the first row is for event 1, which is CV death. The second row is for non-fatal MACE, event 2, and the third row is for non-CV death, event 3. The first two columns are, the first column is control risk, the second column is treated risk. It's hard to see what's happening here, but just the estimates of the Allen-Johansson in red and the TMLE in blue don't seem to be substantially different. Then we can start looking at the comparisons. So let's start with the comparison of non-CV death. We might expect liraglutide not to have an effect on non-CV death, and that is actually what both these estimators show. The risk difference, the confidence, the 95% confidence intervals of both these estimators cover 0 for the risk difference, and they both cover 1 for the relative risk. So something that we might perhaps expect. Moving on, we can look at event 2, the non-fatal heart attacks and non-fatal strokes. And here what we see is the risk difference is bounded below 1, and so and the relative risk is bound. The risk difference is bounded below 0, and the relative risk is bounded below 1. And so both of these estimators show, at least for years 2, 3, and 4, that liraglutide has a benefit with respect to reducing non-fatal MACE events. And then lastly, we have CV death. And here we actually see TMLE, the slight efficiency gain from TMLE playing a nice role here, as the confidence intervals for the risk difference at years 1, 3, and 4, as well as the confidence intervals for the relative risk at years 1, 3, and 4, actually allow us to, TMLE would say that liraglutide has a significant beneficial effect at reducing the risk of CV death, whereas the Allen-Johansen confidence intervals cover 0 and 1 respectively. Yeah, that's these are preliminary results, but what's next is for me to hand this off to Helene, and Helene will then talk about continuous time as well as perhaps how and one-step estimation. Reasons to move towards that direction are that discrete time TMLE can be quite computationally expensive when the number of time points is large, as well as hazard estimation being unstable when the time points become large. All right, and I think that's
great. Let's hand over to Helene, and I know we've cut into your time a bit. So Dr. Redgard, I think use the time that you need, but if we run up to the hour, I think we will, some of us can stay on for questions if that's possible, and that will be recorded, and we'll also be responding to questions over writing. But Dr. Redgard, take it away, and thanks very much for that beautiful talk, David.
Nice. Okay. Yeah. So can you hear me?
We can. Yes.
Okay. I'll try and share my screen, and I'll try to cut a few details as we go along, and just interrupt me if I'm taking too long. But otherwise, I'll just get to it. So yeah, I'll talk about one-step TMLE for continuous time competing risk analysis. And I should just mention before I start that this is work in progress. So if you have any input, then please let me know. Right. So yeah, just as an overview, maybe I can cut that part. That's not so important. But otherwise, what is this about? So what I will talk about here is an idea for a method for competing risk analysis that we're working on. So this is a continuation of the work that I presented at the last webinar, which is work with Frank Eriksen and Mark Wendelin on continuous time survival TMLE, or TMLE for time to event data, so also competing risk. And what I'll present here is applying the ideas about one-step TMLE to a competing risk setting, or a continuous time competing risk setting. So the one-step TMLE was proposed by Mark and Susan Gruber back in 2016. So we should just briefly recap what TMLE is. Then the general template has these 2 steps. So an initial estimation step, where we construct initial estimators, maybe based on a parametric model or a superlearner for important or relevant parts of the data generating distribution. And then we have a second step, so-called targeting step, where we update these estimators to get asymptotic linearity and thus asymptotic normality, and thus inference, and all this efficiency and double robustness and nice things. So one-step TMLE is really another variant of the targeting step. So yeah, the initial estimation step is still the same. I won't say much about that. So just a few words that we'll get back to later. So the idea of one-step TMLE is based on the notion of so-called universal least favorable submodels, which is something that they construct and construct TMLE estimators for in the paper from 2016. And what's really nice is that if we have a TMLE based on a universal least favorable submodel, then we're able to solve multiple score equations simultaneously. And that's something that's very nice, because what we basically want to do is that we want to target treatment effects on cause-specific absolute risk functions for really just multiple causes simultaneously. And what that will give us is inference across causes and inference across time. So that's nice, I think. Today, in this talk, I just wanted to dig into the general idea, try to illustrate it, and I'll try to illustrate the applicability. I have just applied it to the data set that Thomas also talked about, the PBC data, and then I also have some simulations, which I may be skipping in the end due to time limitations. But otherwise, just let's really just establish the setting. So some boring notation here in the beginning. So just a picture of the multi-state model here to the right. So the data set, we would have patients or people of a population who are initially in some event-free state, and then we follow them over time until some cause happens. So in the general setting, we would have J different causes. So we denote by T the event time, so the time till the event happens. We'll have an indicator or categorical variable delta that tells us what type of event that happened. But then this is the ideal world. In the real world, we would also have right censoring. So we observe only the minimum of the time to event and the time to censoring. And we also only observe the right censored version of the this event indicator variable. So the data that we would work with would have the structure, which is just like it always is in continuous time survival analysis or competing risk analysis. We have one row of data for each individual. We have a column that tells us the time till event or till censoring. We have a column that tells us the indicator of event type or censoring at the observed event time. And then we'll have a treatment column or treatment variable A, which is this binary variable that tells us if a person was treated in the before the initial state or in the initial state or not. So A equals to 1 would be treated, and A equals to 0 would be not treated. And then we have a vector of covariates L. So I won't be saying much about L in this talk, but keep in mind that we want to be able to adjust for L to essentially handle potentially non-randomized treatment and informative censoring. Right, so I wanted to have something concrete to be able to talk about this. So I'll be using the PBC data, as I said, like Thomas also introduced. So I'm using the data just directly from R. It's available from the survival package. And just to go over this one more time, then this data set is from a randomized trial with 312 liver disease patients or PBC patients who were randomized to treatment with DPCA, I'm using the abbreviation, and placebo. And then they were followed over time. I think the main analysis in the beginning was to assess the risk on the risk of death. But at the end of the trial, also 19 of the patients had gotten a liver transplant. So as Thomas said, this data set has really been extensively analyzed, and I'm not trying to show anything new. I just wanted to illustrate some things. But just first, in early analysis, there's been different approaches to handle this transplant event. So either was treated as a censoring event, or death and transplantation were combined into one endpoint. So we'll do it a bit differently here and not think about one event type of interest as the one of interest, but really think about them both as equally important. So we have these two different causes, cause 1 being liver transplantation and cause 2 being death. Right, so now we want to get started evaluating treatment effects in competing risk analysis. So I wanted just to get notation straight from the beginning. So this is, of course, a repetition of what we've already seen. So cause J specific hazards. Those are just the transition intensities for moving from the initial event-free state to a state of having experienced the cause J. We're not really interested in making inference for these, as Torben pointed out earlier after Søren's talk, but there are still important building blocks in the probabilities that we are interested in. So we are interested, for instance, in the event-free survival function, which is really the probability of not having experienced any of the event at time t. This can be expressed in terms of all the cause-specific hazards. Again, it's also equal to 1 minus the sum of all the cos j subdistributions, or so-called absolute risk functions, which I denote by fj. So yeah, these are, as usual, the probability of failure due to cos j before time t. And as we've seen so far and is well known in competing risk, these also depends on the event-free survival, and thus also depends on the hazards of all the other cause-specific hazards. Right. So how do we move from here to quantifying treatment effects? Well, so I think this is also just what David talked about, like having this multivariate outcome variable. So this is really how we will do it. So in the general case, we'll just have a j-dimensional variable with elements given by these indicator variables of these point processes, essentially. So njt is the indicator of having observed a failure due to cos j at time t. So this variable just really tells us or gives us information on what state the subject is in at time t. So of course, at time t, j plus 1, different things cannot happen. Either they fail due to one of the causes or no event happened. And then we know that the distribution is just completely characterized by the subdistributions. So just to relate this to the PBC data, so in the PBC data, we just have a 2-dimensional outcome variable that can have 3 different levels. Either no event happened, or liver transplant, or a patient died. And then the distribution is just completely characterized by the 2 cause-specific absolute risk functions. Right. So just before I dig more deeply into this, I just wanted to say that what we propose here now would be essentially, if we're evaluating the treatment effect, then we should do it on this whole vector. So really looking at the distribution of the multivariate outcome variable under treatment and under no treatment, just as David also presented. So what we can do in that framework, we can target the effect on a single cause-specific hazard, but we can also target the effect on a subset of cause-specific hazards, or really, as we will do here in this talk, target the effect on all the cause-specific. Did I say hazard? I mean absolute risk functions. I'm sorry. Then we can also target the effect at 1 or at multiple time points. So I'll move through this in the remaining slides. Right. So we need to define this multivariate target parameter that tells us about this effect. So what I'll do is that I'll just quantify each of the elements of the multivariate target parameter with my notation. So for each cause of interest, J, and time point Tk, and some fixed chosen treatment level, no treatment or treatment, we can define parameter psi ajk as a functional of the data generating distribution to be equal to the cos j subdistribution evaluated at time tk under setting treatment to the treatment level small a, and then marginalized over the distribution of L, or standardized with respect to the distribution of L. And without going too deep into it, then I'll just remark upon the causal interpretation. So if we define TA as the event time for subject, if they had, possibly contrary to fact, been treated with treatment level equal to small a, and likewise the delta A, the event indicator for subject, had they been treated with treatment level a equals to small a, then under usual causal identifiability assumptions that I will not dig into, then this parameter really has this average causal interpretation as the risk of cause j failure before time tk. We would see if everyone had been given treatment level small a. And this is something we cannot do with the hazard, for example. Right. So we'll continue with the statistical parameter, but just keep in mind that we have this interpretation under the causal assumptions. So So now to move on, we choose our target causes, choose our time points of interest, and choose the counterfactual scenario that we're interested in. So we're interested in the effect on the treatment or on the control, or we're interested in the difference of the average treatment effect or the ATE. Right. So I thought for annotational simplicity, I'll just focus first on the setting corresponding to just having two causes, just like in the PPC data from R. And then I'll just only be interested in the average treatment effect of the ATE on both, on the two cause-specific absolute risk functions. So the first parameter, psi1, is the average treatment effect on the absolute risk of cause 1. And psi2, sorry, is equal to the average treatment effect on the cause 2 subdistribution. And then I'm just focusing on a single time point for now. Right, so now our target is really a multivariate parameter. So psi p is just this two-dimensional parameter. Yes, right. So getting started to estimate this target parameter. So this is a usual formula that we've seen a couple of times now here. But we can really represent this, the average treatment effect on either cause is given by the difference between these two treatment-specific parameters, and each treatment-specific parameter can be identified as this expectation of an integral over over these cause-specific hazards, and then integrated out with the specific cause D of interest. So now to get started estimating, we can. As we usually do, we can estimate this outer expectation over the distribution of L just by the empirical average. And then what's left are these conditional cause-specific hazards. So yeah, that's what's left to be able to estimate these two parameters. So just as a summary down here, we need estimators for both the cause-specific hazards to construct an estimator for the effect on F1 and an estimator for the effect on F2. Right, but we don't just want to do estimation, we want to do targeted semi-parametric efficient estimation. So what does it take to go from here to provide an efficient estimator? So what we can note is that we really have two separate estimation problems, the effect on F1 and the effect of F2. For each of these, we can derive the efficient inference function, as David showed, for a discrete time. And then we know that this efficient inference function characterizes the efficient estimator of that particular target parameter. And for this problem, then I won't be presenting the formula, but we can note or maybe remember from David's slides that the efficient inference function depends on not just the cause-specific hazards, but also the censoring survival function, which I denote by SC, and the treatment propensity, which I denote by phi A. And then we know by the more or less usual proof for constructing a semi-parametric efficient estimator for a one-dimensional target parameter that if we can construct an estimator p hat n for these four quantities that solve the so-called efficient inference curve equation or the efficient score equation and some regularity conditions that I will not dig into here, but under these conditions, then we get the usual TMLE benefits. So we can work with large statistical models, incorporate machine learning, and still get asymptotic normality, and we can thereby construct confidence intervals based on the efficient inference function. And we know that the estimator has the smallest possible variance. But to move on from here, we can just note that this was really treating it all separately, and this is really a two-dimensional estimation problem. So this is where one-step TMLE comes into the picture. So just really to distinguish between handling this problem as two one-dimensional problems and then as one two-dimensional problem. So what we would usually do, or what we can do with what methods there exist for semi-parametric efficiency, efficient estimation, except for one-step TMLE, would be to handle the two problems separately. So construct an estimator for one that solves that efficient inference curve equation, and construct an estimator for the other one just as well, but keeping the two completely separate. But we can also handle the two problems simultaneously. And for that, we can use the one-step TMLE, right? So a recap on how a separate way would go. So if we would apply this separate or normal iterative TMLE, then we would start by constructing initial estimators for these 4 quantities, entering the efficient inference function, so the cost-specific hazard, and the treatment propensity and the censoring survival function. Then we would target the effect on F1 that produces 2 estimators, or an estimator for each of the cost-specific hazards. And then they can be plugged in to estimate the target parameter, the effect on F1. And then we would do the same thing for the effect on F2. That would give us a new set of estimators for the cost-specific hazards. And then we would plug those in to give us an estimator for the other target parameter. And then we would now have 2 sets of estimators for the data during distribution, where one solves the one score equation and the other one solves the other score equation. Then we would have marginal inference, so convergence to a one-dimensional normal distribution that we can use for inference. So what's the difference now? Going on to the simultaneous and what we will do with the one-step TMLE. Well, the difference is that instead of having these 2 separate targeting steps, we just have one joint targeting step where we target both parameters at the same time. And now what we get is just one estimator for the quantities that we need, and this estimator solves both score equations simultaneously. Right. So one thing that we get out of this is that we can use the asymptotic normal distribution for inference, or we get convergence to a 2-dimensional mean zero normal distribution that has a covariance matrix given exactly by the covariance matrix of the stacked efficient inference function. So we can use that asymptotic multivariate normal distribution for providing marginal confidence intervals, but we can also use it for providing simultaneous confidence intervals. So essentially, we can provide inference for the 2-dimensional parameter and, for instance, conduct an overall test of no effect on both parameters at once, right? So yeah, I wanted to include something about how this one-step TMLE works. So this will be a bit more technical just for the next 2 slides. But the really important thing is to understand that the one-step TMLE is based on these universal, these favorable submodels as proposed by Mark and Susan in their paper. So just to say 2 words about what that is. Well, for a one-dimensional parameter, we can first look at that. Then in semi-forensic efficiency theory, and particularly you can construct like the regular so-called iterative TMLEs. We talk about these least favorable submodels, which are really parametric submodels, one-dimensional parametric submodels. They go through a given P and then has score function evaluated in epsilon equal to 0 equals to the efficient inference function. And so we would normally construct a TMLE based on this, and then we would have to iterate it until the epsilon is equal to 0, at which point we solve the efficient inference curve equation. And that's why we call it the iterative TMLE. Right. So now we can define a universal least favorable submodel. That's what they define. It's still a one-dimensional parametric submodel, but now this has this least favorable submodel. Not just at epsilon equals 0, but really at all epsilon. So that's why it's called universal least favorable submodel. And now if we construct the TMLE based on the universal least favorable submodel, then the maximum likelihood estimator for epsilon will just directly solve the efficient inference curve equation just by this property. So that's really nice. Of course, our problem now is just 2-dimensional, it's multivariate. A parameter has 2 elements, and the same with the efficient inference function. So here we define the universal least favorable submodel as the model that satisfies that the score is equal to a norm of the efficient inference function. So here in our case, this norm could just be the standard Euclidean norm. Right. So without going into too much detail, I just wanted to show that it's possible to define such a universal least favorable submodel. So here just shown it without going into detail with the notation, but defining it for each of the cost-specific hazards. And then we can note that these really have the property that when we plug them into the likelihood and take the derivative, then we get exactly back the norm of the efficient inference function. So if we can find the MLE, then we know that that one solves the norm of the efficient inference function equal to 0. And then by that fact, we just know that we also solve the two separate score equations. So that's really nice. That takes care of what we wanted, because we've now collapsed the targeting step just into one targeting step, where we get one estimator for the components of the data during distribution that now solves both the score equations. As a side note, we can note that this is particularly nice. We know by fact or by definition that the survival function at any time t is equal to 1 minus the sum of the two subdistributions. So now we know that by construction, the estimator achieved with the one-step TMLE will also solve the score equation for the effect on S. So we just get the effect on S, a targeted estimator for that, just also for free, so to speak. And this is in contrast to, for example, the iterative TMLE, which would have to be run separately again to target that effect on S. So in the end, that could produce really incompatible estimators for S, F1, and F2, because we were not ensured that they would sum up to 1. So I have an illustration of that in a few slides. Right, so how would we do this now? So I just wanted to illustrate the one-step TMLE applied to the PBC data, just as a single time point still. So we use the one-step TMLE to construct estimators for the two cost-specific hazards. We use those to construct estimators for the two subdistributions or absolute risk functions, and we use those two to estimate the target parameters, so the two average treatment effects, simply by plugging them in or taking the empirical average of the differences. And then, as I just showed on the previous slide, when we have the estimators for these two average treatment effects, we also have a targeted estimator for the event-free survival probability at time t naught. So that would just be minus the sum of the two average treatment effects on the cos1 absolute risk function and the cos2 absolute risk function. And then we can note the interpretation that, for instance, if the average treatment effect on the cos1 subdistribution is larger than 0, then that would indicate an increased risk of liver transplantation under treatment. Likewise, with the average treatment effect on the cos2 absolute risk function. Whereas the average treatment effect on survival, if that is larger than 0, then that indicates a beneficial effect of the treatment, namely that chances of, or there are increased chances of staying event-free up till time t naught on the treatment. So here just applied the one-step TMLE to the PBC data, and it's not very interesting because, and I think I didn't mention this earlier, but in this data set, it's really quite well known that there is no treatment effect. So there's nothing to come after here. So it's really just for illustration that I'm using it. But what we can get here is then the effect, or the average treatment effect, now simultaneously for both cos1 specific subdistribution, cos2 specific subdistribution, and for the survival function. So in this column here, so I've just shown the average treatment effects, and we can see, and also see it on the plot, that the 0 is contained in the confidence interval, so there's really no significant effect. We could also look at the treatment-specific probabilities and the placebo-specific probabilities. So for instance, the middle column tells us the risk and the survival we would observe if everyone in the population had been treated. And what's really nice with the one-step TMLE is that we're really sure that these two columns will sum up to exactly 1, because we have constructed it with compatible estimators. So we really respect this model constraint that the F1 estimator plus the F2 estimator plus the survival estimator should equal 1. So that's one thing that we get out of it. I still have 5 minutes, maybe. I'll say something briefly here. Nice. Okay, so I just wanted to briefly mention the general setting because we're really not confined to 2 causes, and we're not confined to 1 time point. So we, in the general setting, we could have j different causes and k different time points. And what that would take was simply to increase the dimensionality of the target parameter, and thus also the efficient inference function. So we simply just stack together all the different effects across time and across causes. And then we can now use the one-step TMLE to construct estimators for all causes j and all time points tk. And these are constructed all with the same estimator for the data generating distribution, or the components of it that we need, such that we solve the separate score equations, but we solve them all simultaneously across all the causes and across all the time points. And then we get convergence to the multivariate normal distribution with the covariance matrix given by the covariance matrix of the whole vector of stacked efficient inference functions. And we can, for instance, use that to construct the simultaneous confidence intervals. So really providing inference for this whole multivariate parameter across all causes j and time points tk. So just on a side note, that for instance give us a quite good method for testing multiple hypotheses and correcting for multiple testing, improving on methods just like Bonferroni that doesn't take into account the correlation between parameters, in which we can do with this method. Yes, so then I just wanted to apply this to the PBC data to show, and again, there is no effect, so it's not something, there's no new conclusion based on these data or anything, but just to show that what it is that we get out of this. So here just applied it across 30 time points. So we see the cause1 absolute risk function to the left, so the risk of liver transplantation. In the second column, we see the risk of death, and then in the last column, we see the event-free survival. And compared to doing this separate targeting or the iterative TMLE, then what we get here for free, more or less, is monotonicity and compatibility. Yeah, so I just wanted to illustrate what I mean again by that. So for compatibility, we wanted that the subdistribution 1 plus the subdistribution 2 plus survival is equal to 1. And if we look here at the lower left corner, then we see the one-step TMLE. This is just, it fulfills this constraint like it should. Whereas the iterative TMLE in the upper left corner, it looks nice for a small length of follow-up, but then when time really progresses, then we see that this model constraint is really not fulfilled. In the right column, I've just tried to illustrate this monotonicity problem, because we know that the survival function is monotonely decreasing and the subdistribution are monotonely increasing. But if we zoom in, for instance, here on the treatment-specific cost2 absolute risk function, then we see that the iterative TMLE is really not monotone. So it doesn't respect this model constraint, whereas this is just fulfilled by construction of the one-step TMLE. Right. So, yeah, do I have more time?
You have 2 minutes. Go for it.
I have 2 minutes. Okay, I can go over a simulation in 2 minutes. That's good. So I just wanted to include also simulation just to show an example where there is an effect, because there is no effect in the PBC data. So here I just I have a simulation study where I have 3 competing causes. And then my treatment has no effect on the cause1 hazard, but it does have an effect on cause2 and cause3 specific hazards. And then I have covariate dependent treatment and censoring, just to make sure that we're all along that this doesn't only work in randomized trials. And then we can note that treatment which reduces the hazard rate of a competing event indirectly increases the risk of the event of interest. So this is what we can illustrate with the simulation setting. So I'll just apply the method in a single data set, targeting the average treatment effects on all absolute risk functions. I'll do it both at a single and then at multiple time points. And then for estimation, I'm using this ensemble Cox superlearner for initial estimation of the cause-specific hazards, and then I'll use the one-step TMLE. Yeah, so We could first just look at the effect at a single time point. So here, just look only at the COS1 subdistribution or absolute risk function. So here we would see that looking only at that, we would see that increased risk of COS1 events simply due to the decreased hazard of the other competing events. So here it would really give us a much better picture of what's going on if we also looked at the effect on the other subdistributions and also on the survival distribution. And we can also go even further and look at the effect across different time points. So here I just applied it with 5 time points, and then I here added the simultaneous confidence intervals. So this just altogether gives us a more full picture of what's going on in with our data, and tells us really the probability of everything that can happen to a person in our data set. Yes, right. So final slide is just a very brief concluding remarks. So I hope I've been able to illustrate that this one-step TMLE gives us a framework where we can really, if we want to, report the full story for computing risk analysis. And what we, for example, get out of it is that we're ensured to fulfill the model constraints or the parameter space constraints. We have monotone curves, and we know that the subdistributions and the survival functions sum to 1. And then we get this whole multivariate inference and multivariate efficiency. And then we still get all the things that we normally get, of course, with TMLE. So we can still combine flexible learning with valid inference, and we can incorporate machine learning, and we get efficiency and double robustness. Right. So yes, thank you for listening.
Thank you, Dr. Redgaard, and thank you to all of our speakers. So I know we're close to the hour, and I think moving forward, we will build in future webinars a bit more time for questions. I think we do have just a couple minutes now, so feel free to type any questions into the chat. I'll also just put up our coming up session. So our next session will be April 7th, and we'll be speaking about developments in longitudinal mediation analysis and clinical applications. And then the following 2 sessions will be on an overview of methods for integration of observational and randomized data. And then finally, looking at applying this causal roadmap to the specific problem, looking at dynamics between diabetes and dementia using both the health registry and randomized control data. So I will just move to the chat. Any question? So we had a question from Torben, maybe for the last 3 minutes. And again, I want to thank all of our speakers for really giving us a beautiful overview of first the importance of framing the question in the context of competing risks, and then really taking us through some of the advances in currently available software in ways for going after really these cause-specific absolute risk functions over time, and ways of contrasting them. So lovely job. Torben, maybe take it away.
Maya, maybe yes. I should answer Christian's question first.
Oh, yes, sure. So there was an earlier question from Christian. Can you read it out loud?
Yes, the question is, in risk regression, what if treatment is discontinued for some individuals? Then what would you estimate? So the first answer is, in my package, you cannot deal with this problem. And the second is, you want to hire Maya to walk you through the roadmap, and I can tell you it will take several weeks, but at the very end, you will have a very nice solution.
Thanks, Thomas. Torben, did you want to pose a question to Helena and David?
Yeah, very nice talk to both of you. My question goes to that I sort of agree that you can sort of give us the full story because you go for all the cumulative incidence functions, but maybe it's too much. Or my point is that we may need to sort of disentangle the effect that we are sort of interested in communicating, because you get all these cumulative incidence functions, you can compare the different groups, but at the end of the day, you need to communicate some sort of conclusion to the public or to the client, and that may be quite difficult, I think. And I also noticed, Helene, when you set up the simulation study, you said that you said the effect of the treatment, but that you modeled through the cause-specific hazard function. So if that is what we mean by the effect, then maybe that was what we should go for. But then we are back in interpreting causal hazard ratios. So I think there's still a need for sort of disentangle the effect that we are after, and I don't have the answer. We have looked at this separable direct and indirect effects. There's sort of a suggestion towards the solution. Yeah, it was a comment or a question.
Thanks for the comment, Helene, and then David, do you want to comment? And then as well, anyone else? For example, Mark's on the call as well, might wish to comment.
I can say first that maybe my language was not so good when I said the effect. I meant the effect on the cause-specific hazards. But otherwise, I agree fully, Torben, and I think it's very interesting what you're doing with the separable effects, because sometimes we are interested in reporting one effect estimate, and that maybe we can do that with your separable effect. Yes,
yeah,
I think
because all cause-specific hazards enters every cumulative incidence function. So,
yes.
Yeah.
Yeah. Let me. Yeah, I don't really have anything more to add. I don't think it's a good point. Looking at all of the risks for every event, especially if there's lots of events, it's a complicated story. And yeah, trying to simplify that, it's just difficult.
I might add in that I think there's probably not going to be one answer, right? As there always isn't for these sorts of things. And that it all comes down to starting up. It's the roadmap again, but like for a given question and a setting, what is the relevant question? What is the relevant estimand? What causes do you care about? Which contrast do you care about? There won't be one answer, but at least there's a template for both laying out the answer or laying out the question that you want to ask, and then being able to answer it and not getting into this situation that we have competing events. So we use the specific estimator. So then this is the thing we get out. So that must be what we're interested in. I do think that it's been a really nice illustration from all of the speakers of like the ability to kind of move forwards in the roadmap and sort of start with your question. But I absolutely agree. I think what are the questions is one size fits all, but also I think there's additional interesting work to be done there. Absolutely. So thanks for that comment as well, Torben. We have another question. If you have quantities that sum to 1, you must report all of them from. So this is I don't know, Helene, do you want to comment on that? I think this is just speaking to your final.
Yeah, if I understand.
It's basically saying that the last drawing you showed is the one you need to show. It's very difficult for people to do the subtraction in their own heads.
Mm-hmm. Yeah, so we should report them all, but didn't I report them all?
You did, but Torben suggested otherwise.
Torben suggested that we should really not go maybe in all applications for all the different curves and effects on all the different subdistributions, but maybe defining a new target, which is what he has proposed.
Yeah, let me just say it.
That's what I disagree with. So I would support your way of doing it.
Ah, you're okay. You're supporting. Yeah, sorry. Thanks, then.
So I will make a final point, but yeah. So I think the key is here that these subdistributions across treatment and across time is really all there is. And now we have a TMLE which can target that simultaneously, giving you a completely compatible estimator, fully efficient with inference, simultaneous confidence interval, everything. Now, what you're going to look at from all of that is then up to you, right? But anything you compute from that comparison will be covered by this TMLE. You just evaluate and you have the corresponding inference. So there's nothing lost. You have it all. And now you have the problem of saying, okay, how do we communicate this? And you can look at features of that comparison. And some are obvious, and some are maybe, and there some cleverness might be helpful there to communicate things about that. But that's how I think of it. So I should say I like the fact to report it all, because this is the real story. This is the experience of the patient under treatment, under control. This is what the multivariate process looks like, and we have a corresponding inference. And yes, life is often very complicated, and it might not be easy to communicate this, but this is the reality. And I think we can then spend time to think about what it all means.
But I mean, I think they're not mutually exclusive, right? So you have all of that, you report all of that, but there's still space, I think, to say for a given application, what's the most interesting summary, right? And how do you interpret it? And so I think both, right, are quite.
So I said it is all there, and now you can still figure out the best summaries to report. Exactly right.
But any other? I know we're 5 past the hour. It was really, I think, a beautiful series of talks that, you know, were we not on different time zones and able to have a bit more time, I would love to continue, but I know everyone's past the hour. If there are any more questions, please feel free to type them into chat. Otherwise, please feel free to follow up offline, and please join us for our next seminar on longitudinal mediation on April 7th. I think we'll be making all of these slides available as well, and there's a lot there that we went through quickly in terms of practical implementation of these methods with software. So wonderful to see everybody. Thanks for hanging in there, and we look forward to seeing you again soon.
Bye.
Bye.
Bye.